His research interests are in quantum algorithm, quantum computation, and quantum walks. And today he will be talking about implementing linear combination of unitaries on intermediate term quantum computers. Dr. Chakraborty.
Yeah, thank you, Dr. Mazumdar, for the kind introduction, and thank you to the organizers for the invite. I hope you can see my screen and I'm audible and everything. You can see this pointer. Can you please give me a confirmation? Yeah,
Yes,
okay.
yes.
Okay, so I'll also thank the organizers, especially Professor Panigrahi, for organizing a conference of this scale and scope. I think it's extremely beneficial for PhD students, postdoctoral researchers who are doing their work in India. It's my first time giving a talk here, so I would really like to congratulate you all. Okay, so I'm going to talk about this framework of linear combination of unitaries, which is well known. It's a very general quantum algorithmic framework, which is used for designing several quantum algorithms. And the goal of this talk is to implement this framework on quantum computers that are not necessarily fully fault tolerant. So I'll consider quantum computers that are that have certain restrictions. So circuits have certain restrictions. The ancilla space has certain restrictions. And I'll still try to see if there's a way to implement this general quantum algorithmic paradigm. Okay, so that's the framework of the talk. So I'll start by, discussing the era of quantum computing that we are in currently. So as all of you know, we are in the so-called noisy intermediate scale quantum era of quantum computing, right? So where the quantum devices that we have, they have a limited number of noisy qubits. So you don't have a lot of qubits. You have a limited number of noisy qubits. The quantum circuits that you have only a short limited depth, right? And you cannot make perfect measurements, so it's kind of noisy, right? So everything is noisy. And so over the past few years, people have been trying to develop, quantum algorithms using these devices, the so-called NISQ devices. However, all these algorithms, for useful problems at least, share this property in that they are heuristic, right? So provable performance guarantees are absent in the NISQ framework. So you generally, typically, you devise a strategy, you run it for some fixed number of qubits, right? And then you kind of heuristically say that okay, it does better than classical algorithms for that particular size, and so on. So provable performance guarantees are indeed absent in the NISQ era. And so here I've shared this plot from John Preskill's paper, which kind of reviewed NISQ from 2018. And this paper was published in Quantum in 2018. And what John Preskill said that, within 5 years, if you can look at the plot, which is right about now. So within 5 years is 2023 from 2018, we'll be transitioning away from the NISQ era, right? So the question is, all right, so you had the NISQ era, which was useful in the sense it helped us understand the power of these noisy quantum devices. But indeed, the drawbacks were that the quantum algorithms that were designed did not have a provable speed up, right? So on one hand, we had this NISQ era, which we should be currently transitioning from, and on the other hand, we have this fully fault-tolerant quantum computer, which are decades away, right? So the motivation for this talk is essentially what comes in between. So as we transition from the NISQ era, what kind of devices do we have, and can we implement generic quantum algorithmic paradigms with a provable quantum advantage on these intermediate devices? All right, so that's the basic framework of the talk. Okay, so indeed, so we are currently in the NISQ era, and we want to go towards full fault tolerance, which is kind of decades away, depending on where you are, how optimistic or how pessimistic you are. Let's assume for the argument's sake that it's still kind of a decade or two away, right? So what is there in between, right? So what's there in between is this framework of early fault-tolerant quantum computers. Okay, so one of the possibilities of quantum devices that will become available after the NISQ era are the so-called early fault-tolerant quantum computers, right? So what are these devices? Well, these devices share a lot of similarity with NISQ devices in the sense that they won't have the capabilities of a fully fault-tolerant quantum computer. So these quantum devices will still have short depth quantum circuits. So the circuits will have limited depth, and the number of logical qubits that will be available are going to be limited. So indeed, you won't have access to too many ancilla qubits to perform your computation. Well, the point of departure from the NISQ era is that although limited, you will have a few logical qubits, so a limited number of logical qubits. So essentially, you no longer suffer from noisy qubits, but at the same time, the experimental capabilities are not advanced enough to develop fully fault-tolerant quantum computers. And so you will have short depth quantum circuits, and also, very access to very few ancilla qubits, right? So for instance, just for illustration, consider a quantum circuit like this. Here, V1, V2 are unitaries. And so see that you have this ancilla space of m qubits, and at each step of your computation, you are applying this controlled unitary. Note that this controlled operation is controlled over all the ancilla qubits. And this is a pretty deep circuit, right? So having quite a large number of controlled unitaries. What we argue is that in this early fault-tolerant regime, this kind of circuits are not allowed. So you cannot have deep quantum circuits that have sophisticated controlled operations. Okay, here O is essentially measuring, you are measuring the expectation value of some observable essentially. All right, so these kinds of circuits are not allowed. So you may have circuits of this kind which are short depth, so applying only a few unitaries. You maybe have access to only a single ancilla qubit, and this controlled operations are controlled over that solitary ancilla qubit. And these are small quantum circuits, right? So you are restricted in the early fault-tolerant regime by these sorts of quantum devices. Okay. Now the question that we ask for this talk is, can we design useful quantum algorithms using these devices? Okay. So what should these algorithms have? What features should one keep in mind while designing quantum algorithms for these devices? Well, there are two broad properties. First of all, because we are in this early fault-tolerant regime, our goal would be to actually minimize the quantum resources that the algorithm consumes, right? So what does this mean? So you would look to run quantum circuits that have short depths. So that you can limit the total coherence time, right? So it's better to say, for example, have order of t runs of a circuit of depth d than one run of a circuit of depth td. So that's one example, right? So you run a short depth quantum circuit for many times, many classical repetitions of this short depth circuit is allowed, because classical repetition is not expensive, right? So we expect that you can reuse this short depth circuit several times, as many times as you need. But to run deep quantum circuits is going to be impossible in this regime. And the other feature of these algorithms, which kind of also differentiates it from NISQ algorithms, is that these algorithms should be reliable, in the sense that you should be able to provide provable performance guarantees. So no heuristics here. Your algorithm should have a definitive running time within which it should be outputting the quantity of interest. Okay, so these are the two distinctive features of quantum algorithms for early fault-tolerant quantum computers. And one possible strategy would be indeed to repeatedly sample from some short depth quantum circuit. So you take a short depth quantum circuit, you run it, you get some outcome, and then you rerun the circuit, this short depth circuit, several times, and then you get a bunch of outcomes, and then you do some classical post-processing with the data that is output by this short depth quantum circuit. All right. So this could be one strategy to design quantum algorithms using these computers. Okay, so indeed, in the recent past, there have been a few quantum algorithms for that are tailored to early fault-tolerant quantum computers, and they have been mostly for designed for one particular problem, which is ground energy estimation. So suppose you have some Hamiltonian and you want your quantum algorithm to estimate the energy of the ground state of this Hamiltonian, right? So indeed, groups in Berkeley, in Zapata, in France, in Caltech, they came up with strategies by which you can estimate the ground energy by using early fault-tolerant quantum computers. All right. So the question that we are going to ask in this talk is, all right, so there are these limitations for early fault-tolerant quantum computers, but even then, can we leverage these systems to implement generic quantum algorithmic paradigms? So what I mean here by generic quantum algorithmic paradigms is that, if you look at the field of quantum algorithms, there are a few quantum algorithmic techniques that seem to be appearing at many places. So if you can, if you can implement that particular technique using these early fault-tolerant quantum computers, you will open the door to develop several quantum algorithms in this paradigm, right? In this using these devices, right? So this is what we explore. So we ask whether we could implement any such generic quantum algorithmic paradigms with using these early fault-tolerant quantum computers. All right. And the framework that we indeed implement in this talk is the framework of linear combination of unitaries. Okay. So what is this framework for people who don't know? Well, linear combination of unitaries is a widely applied framework used in the development of several quantum algorithms. And the idea is the following. So suppose you're given some Hermitian matrix, let's say Hamiltonian, and some initial state psi 0, right? So this procedure, this technique, this algorithmic technique applies those functions of the Hamiltonian to your initial state, which can be approximated by a linear combination of some unitaries, as the name suggests, right? So you would want to implement some f of h to your initial state, where f of h can be approximated by a linear combination of unitary operators. All right. And indeed, across several areas, you find that this is the case. So for many different applications, ranging from Hamiltonian simulation, solving quantum linear systems, ground state preparation, optimization, quantum walks, in all these cases, at the end of the day, they boil down to applying a certain linear combination of unitary. So by the way, here, by the function of a Hamiltonian, what I mean is you're implementing the function f to the eigenvalues of your Hamiltonian. So suppose your Hamiltonian has eigenvalue lambda, you're implementing, you're transforming by this operation the eigenvalues to f of lambda, right? So that's what I mean by implementing a function of the Hamiltonian. Okay. So for a wide range of these problems, indeed, you see that the underlying technique boils down to applying some function f, which can be approximated by a linear combination of unitaries. Okay. But the standard technique, the technique that is generally used to implement all these frameworks, the LCU framework that is used to implement these algorithms are only useful for fully fault-tolerant quantum computers. And why is that? Well, that is because they don't. Implementing LCU is difficult. It requires deep circuits. It requires sophisticated controlled operations. It requires several ancilla qubits, which may not be available to you in the intermediate term that I just described in the previous slides. All right. So let us look at the standard approach. So for the standard approach to implement LCU, as I mentioned, we want to implement some f of h to your initial state psi 0, right? So the first thing that you need to do is you need to prepare your ancilla qubits. So these are your ancilla qubits in some special state. Okay. And here lambda is essentially the sum of the coefficients. All right. It's essentially the sum of the LCU coefficient Cj that you see here. Okay, so you need to, you need a unitary that initializes your ancilla space. So you need M, which you can think of as log of capital M, which is the total number of terms of your in your LCU, right? So you need an answer to set up an ancilla space, and more importantly, you need to apply a unitary, which is a controlled unitary, and this controlled unitary is controlled over each of these ancilla qubits. All right. So as you can see, this is quite expensive and difficult to implement in the intermediate term. So if you look at the quantum circuit, well, you need this ancilla space, right? And you need your some unitary to initialize your ancilla space, and then you apply a sequence of all these controlled unitaries ULs, and and this is a very, very deep circuit. All right. And then what we do is we kind of we see that you may implement, following implementation of the circuit, you implement several rounds of amplitude amplification, which adds to further cost, and in the end you will be able to prepare a quantum state like this. Okay. So if you look at the transformation, it's essentially this transformation is doing what the circuit is supposed to. So if you initialize the ancilla register, apply the controlled unitary, apply a dagger of this initial unitary, then you end up in a quantum state like this. Okay. Now, for linear combination of unitaries, one thing that I forgot to mention is that we have access to these UJs. Okay, so we assume that we have access to these UJs. That's kind of a precondition for implementing linear combination of unitaries. And so what we see is that by implementing this circuit, we prepare a quantum state, which is kind of sum over JCJ UJ divided by this lambda parameter, which is the sum of all the coefficients. So it's essentially sum of J CJ. That's the lambda. All right. So we do prepare a quantum state in the second register, so that wherever the first register is in 0. So our final state is 0 on the first register, and the required state sufficiently subnormalized plus something that has no support on 0. All right. So this phi perp is orthogonal to this. Of course, this state is not normalized, right? Because if you want to normalize this, you have to multiply and divide by the norm of f of h applied to C0 and so on, right? And so if you are indeed interested in preparing this quantum state phi, you need to apply, as I mentioned, several rounds of amplitude amplification, which adds to the cost of implementing LCU by the standard procedure, right? So this is what you need. So please remember this quantum circuit as I move along in the talk. It requires several ancilla qubits. It requires deep quantum circuits. It requires sophisticated controlled operations, and it also requires amplitude amplification. All these things are expensive and not available to you in the intermediate term. All right. But indeed, also just preparing phi, this LCO state is not interesting, because in most practical scenarios, we would like to predict properties of the state phi. So for example, if you think about quantum linear systems, you prepare a quantum state which is H inverse psi 0 divided by the norm. But this is a quantum state whose entries are amplitudes, right? So their amplitudes correspond to the solution of the quantum linear system. So you don't have access to the classical vector like you do in the classical linear systems. So then what do we do with this quantum state? Well, we predict properties of this quantum state. Think about ground state preparation. You prepare the ground state, right? But then you are interested in, say, some properties of this ground state, like, does this ground state undergo some phase transition? What is the entanglement of the ground state? What is the direction of spins in the ground state? So these are some of the properties that we are ultimately interested in finding out. And so the task often that we are interested in is not just preparing phi, but estimating the expectation value of phi with respect to of some observable with respect to phi. All right. So for this, if you prepare phi using the standard LCU procedure, this is not going to be enough. You need to run the standard LCU procedure several times to estimate the expectation value that you want. All right. And despite these drawbacks, the LCU procedure is very, very useful, as I mentioned, right? So for all these applications, we need to implement specific functions of the Hamiltonian. So for quantum linear systems, f of h is h inverse. For Hamiltonian simulation, it's e to the minus iht, and so on. And in all these cases, you can show that f of h approximates some linear combination of unitary. All right. And so despite these drawbacks, if you gave me a fully fault-tolerant quantum computer, the procedure of LCU was going to be very, very useful, right? It's just that we have a long time to reach full fault tolerance. And so what we would like to do is implement LCUs using early fault-tolerant quantum computers. And so for that, this standard approach does not work, all right? So this is the question that we ask in this talk. Can we still implement this generic quantum algorithmic framework using early fault-tolerant quantum computers? So we using circuits that have limited depth, that have using only a single ancilla, and yet design algorithms that provide performance guarantees. All right, so that's going to be our goal. And before going to that strategy which we use in this paper, let us try to formally define what is meant by implementing an LCU. All right. So as I mentioned, suppose you have some Hermitian matrix, say a Hamiltonian H. We are interested in basically implementing some function of this Hamiltonian, which is gamma close to some linear combination of unitaries. And this norm here is the spectral norm. The details are not important of what kind of norm it is, but the requirement is that the function that you want to implement should be close to a linear combination of unitaries, and you want to have access to these unitaries, right? So using these unitaries, you want to implement f of h, right, to your initial state, right? So without loss of generality, these coefficients, these weights of the unitaries are, you can assume that they are positive real numbers. There are strategies to get around this in case they are not. I'm not going into that. And lambda is essentially the sum of these weights. All right. So the first observation is that whenever you have such a description, so whenever you have a linear combination of unitaries, there's something interesting that you can observe. All right. So the LCU description itself results in some sort of an ensemble. And what kind of an ensemble? Well, for every unitary uj, you can associate a weight, right? And that weight is Cj from this description, right? But you can now divide Cj by the total number of weights to get a probability, right? So every unitary is associated with a probability. So let's say unitary uj is associated with the probability Cj over lambda, right? And then you can use a classical algorithm to sample unitaries according to this distribution D. So you can run a classical algorithm that outputs an integer j with probability Cj over lambda, right? And based on the outcome j, you implement the unitary uj, right? So whenever you have a linear combination of unitaries, you have the ability to generate this ensemble from which you can sample unitaries from. So this is going to be an important aspect of our algorithm that we are going to design, is that we'll be using classical sampling to sample unitaries according to this distribution, a distribution that is proportional to the distribution of its LCU coefficients, right? Okay. So having discussed this framework, let us look at what problem we are solving. All right. So suppose you are given some initials, given some Hermitian matrix, some Hamiltonian H, some initial state rho 0, and some observable O. We develop some randomized quantum algorithm that outputs two quantities, mu and L tilde. All right. And these quantities, if you divide them, so if you output mu over L tilde, it approximates this quantity. All right. So what is this quantity? Well, if you look at just the numerator of this ratio, it is just, if you just look at this part, f of h rho, f of h dagger, it's just the LCU applied to your initial state, right? Trace of O of that is basically the expectation value of the observable. And of course, you would want a normalized quantum state. So the denominator is just the norm of the resulting quantum state, right? So this is basically trace of O rho, where rho is, your the state that you have prepared by LCU, right? So this is what we are interested in. We want to give a randomized quantum algorithm tailored to early fault-tolerant quantum computers that allows us to estimate the expectation values of observables with respect to quantum states, which are kind of which correspond to applying f of h to your initial state, right? Now, for simplicity, let us first focus on the numerator. Let's forget about the denominator for now. Let us just focus on the numerator. So for that, we'll first, give a quantum algorithm, randomized quantum algorithm that approximates the numerator. So it kind of finds trace of O, f of h, rho 0, f of h dagger. All right. And to recall, this is not normalized. To make it normalized, you have to divide by the norm. Okay, so we'll come to that later, but let's first focus on the estimating the numerator. All right. Okay. So recall the quantum circuit that we needed for the standard LCU procedure. It was very deep, had a lot of ancilla qubits, required sophisticated controlled operations, and so on. What we claim is that we'll be implementing this quantity, right, the expectation value of observables, by using just this simple circuit. So here we require only one ancilla qubit, which is in the state plus, so 0 plus 1 over square root 2. These V1 and V2, I'll come to what these are in a bit. And these are just controlled operations controlled on a single ancilla qubit. So this is like controlled on one. The hollow circle here means, the open circle here means that it's controlled on 0. So it's just, implementing these two unitaries. And X tensor O here is just, X is the Pauli X matrix, right? So you measure these are just measurements. So you measure the first, the ancilla qubit in X, and while the second register, you measure O, right? So you can also do this measurement separately. You don't need to measure X and O jointly as this diagram suggests. You can first measure X and then measure O. That is also allowed. And for this kind of a quantum circuit, we draw inspiration from this work by Feierman, Studner, Kuhn, Kifarova, and Isert, where they use similar circuits to implement some quantum simulation algorithm based on multi-product formulas. All right. So what we'll claim is that this simple circuit is sufficient to estimate this quantity that we are looking for. All right. Okay. So our strategies are going to be the same as I mentioned, right? So we'll repeatedly run this short depth quantum circuit and we'll get some outcome. So based on the series of outcomes that we get by repeatedly running the circuit, we'll do some classical post-processing, right? So what are these? Now we come to what these V1 and V2 are, right? So V1 and V2 are basically outcomes of this classical sampling that I just mentioned. So you sample unitaries uj according to this distribution, right? So let's say and these are going to be IID samples. So you sample once, you get some unitary V1, you sample again, you get some unitary V2. So these are different UJs that you are getting, right? So you take two such UJs and you implement V1 and V2 controlled, and controlled on 1, controlled on 0. That's it. So you don't need to implement all these sequences of U1, U2 up to UM as you needed in the standard LCU procedure. Here you're just sampling two unitaries according to these distributions, and then you're implementing controlled versions of them controlled on only one ancilla qubit, right? So that's the quantum strategy that we're using to implement this on early probabilities. As you think, far less ancilla qubits, only one. It has, essentially no sophisticated control operations, and the quantum circuits are also of shorter depth. All right. Okay. So the key insight is that if you sample these unitaries, right, V1 and V2 according to this ensemble, the expectation values of V1 and V2 are simply the linear combination weighted by this lambda factor, right? Because you sample uj, each uj according to Cj over lambda. So the outcome of your sampling is going to be just, expected value, which is sum over j, Cj, uj over lambda, right? And the numerator here is kind of the LCO that you want to implement, right? So that's the key trick here. Okay. So now let us discuss the algorithm. The algorithm is pretty simple. It's just following what the quantum circuit says. So suppose you have your initial state rho 0, and so you prepare plus tensor rho 0, right? So plus is your single ancilla qubit, and then you obtain these samples V1, V2 according to D, right? So once you do that, what you do is you run this quantum circuit, right? So you run this quantum circuit. So controlled on 1, you implement V1, controlled on 0, you implement V2, and so on. And then you perform a measurement of X tensor, right? And then you get a transformed quantum state, rho prime, right? And then that's it. Then what you do is once you make the measurement on this transformed quantum state, you get a number, right? Let's say for the jth iteration, that number is mu j, right? So for every iteration of this short depth quantum circuit, you're going to get a number, right? So mu1, mu2, mu3, so on, right? So what you do at the end of t runs is you take kind of sample average of what you have multiplied by the square of the weight. All right. And if we'll show that if you repeat this enough number of times, this mu is going to approximate this quantity. All right. Okay, so why does this work? Well, the key insight here is that the outcome of the jth iteration of this algorithm is something like this. So this requires a bit of work. It's just two, 3 lines of calculation. You can show that the outcome of the jth run of the algorithm is simply this. Okay. Now remember that expected value of V1 and expected value of V2 are just this linear combination of unitary divided by lambda, right? So what is the expected outcome of this algorithm, of each run of this algorithm? Well, it's basically this quantity, right, divided by lambda square, right? Because these unitaries V1 and V2, their expected values were W by lambda, where W is basically this linear combination of unitaries. Then this quantity is just the expected value of the outcome is just trace of O W rho W dagger, where W is the linear combination of unitary divided by lambda square, right? So that's the key insight. So your expected outcome multiplied by lambda square is something that is pretty much what you want to implement, right? So that is why what we do is we run this experiment once, we get some mu j, and then we run this again and again so that the sample mean, so let's say we run it t times, t should be large enough so that the sample mean converges to the true mean. And there are quantities that give you what t should be, right? So this is familiar to most of you. Okay, so that's our strategy. Short depth quantum circuit, run it once, run it twice, run it thrice, run it t times, take the sample average of the outcomes, multiply by lambda square, and bang, you have what you need to accuracy epsilon. All right. So what is the cost of running this algorithm? What is the cost of each run of this algorithm? Well, the cost of each run is will basically be the cost of implementing V1 and V2, right? And V1 and this V1 and V2 depends on the UJs, right, that you want to implement. And these UJs are going to have their own circuit depths. They'll have their own cost, right? So for any run of the algorithm, the maximum, if the cost of any of these UJs is upper bounded by tau max, then the cost of each coherent run is just, the state preparation cost, then 2 times the maximum cost of implementing the unitary, right? This is pretty simple because any UJ's cost is upper bounded by tau max, so the total cost is going to be 2 times implementing similar unitaries, so 2 times tau max plus the state preparation cost, which is tau of rho 0, right? Now, how many times do you need to repeat the algorithm? And there's also a robustness parameter gamma. These things are we'll discuss in the next slide. We basically, for that, we prove a general theorem in the paper, but it's not. I'm not going to prove it here. The essential thing is that there exists some gamma, precision parameter gamma, so that if you repeat the algorithm enough number of times, the scaling is as lambda to the power 4 and 1 over epsilon square, norm of the observable square, and so on, then indeed the algorithm outputs some mu, so that it is epsilon close to what we intend to estimate, right? So this is the number of times you have to repeat the algorithm, and the cost of each run of this algorithm is basically this, right? So these are the 2 things that we need to keep in mind. Okay, but so far I've only told you about the numerator. What about the denominator? There was a denominator as well, for which we needed an estimate of the norm. Well, interestingly, the same algorithm can also be used to estimate the norm. Why? Because once we estimate the numerator, if the norm is L, we just divide it by L square, right? Divide whatever we got by following the previous strategy by L square to kind of find the expectation value with respect to the LCU state, right? The normalized quantum state, all right? And the way we do this is, if you set O to be identity, so if you repeat the same algorithm, but just set O to be identity, you see that the algorithm estimates norm, right? Then for the whole strategy, where you want to actually estimate expectation values with respect to normalized quantum states, the whole strategy is simple. You run the algorithm twice. First, set O to be identity. In that case, you have a good estimate of the norm, and then run the algorithm again, and just like I had described, and then this will give you an estimate mu, and then you get 2 quantities, mu and L tilde. Then you take their ratio, and this ratio is going to be close to the expectation value you want to estimate, right? Okay, the interesting fact is that this requires, so this algorithm works even when you have no knowledge of what the norm is. Okay, so even if you have no knowledge of this quantity, the algorithm still works. And what we can also show is that even if you had exact knowledge of this quantity, your cost would have been no different. The asymptotic cost would have been no different from what we get. Okay. All right. So we apply this algorithm to 2 problems. As I mentioned, LCO is widely used and it is widely applied. In this work, we applied to 2 problems of very general interest. One is the problem of ground state property estimation. So for example, suppose you're given some Hamiltonian with some unknown ground state V0. You want to estimate the expectation value of some observable with respect to the ground state, right? So that's one application. And the second application that we give is solution of quantum linear system. So suppose you have some initial, some Hamiltonian and some input state B. What you would like is, if X is the solution of the quantum linear systems, which is H inverse B by norm of H inverse B, then you would like to output an estimate of the expectation value of O with respect to the solution of quantum linear systems. All right. So I'll describe these applications very quickly. I don't have that much time to go into too much detail, but I'll still give you a idea about these applications. Okay, so first let us come to ground state property estimation. All right. So this is a very hard problem, complexity theoretically hard problem, even for a quantum computer. The generic problem is actually pretty hard. So the trick is that generally quantum algorithms for this problem take certain assumptions. So what are these assumptions? Well, the first assumption is that you have a good knowledge of the spectral gap, right? So this is the gap between the first excited state and the ground state, right? So let us denote it by delta. And you could prepare an initial state that has a reasonable overlap with the ground state. So these kind of two assumptions that you need, right? So information on the spectral gap delta, and you have access to an initial state, or you can prepare an initial state that has an at least eta overlap with the ground state, right? These assumptions are standard, and they are taken across all quantum algorithms designed for ground state preparation, property estimation, precisely because the generic problem is kind of QMA hard. And by QMA hard, you can think of it as the quantum version of the complexity class NP. Okay, QMA is the quantum version of NP, and so it's kind of the quantum version of NP hard, right? The generic problem. Okay, so these two assumptions make the problem feasible. So it is possible to design quantum algorithms to output quantities of interest in a reasonable time. Okay, so what is the strategy that we take? So the first thing that to notice is that given this initial state psi0, right? Suppose you are able to implement this function of your Hamiltonian f of h, which is kind of e to the minus t h square. So you can think of it as a Gaussian operator. So if you can indeed implement this operator such that t is greater than 1 over the spectral gap square times some log factor, as long as t is greater than this, then if you are able to implement this function, the resulting state is going to be epsilon close to the ground state. Okay, so this is the first observation. So what this boils down to is using LCU to first find an LCU decomposition of this function, and then using our strategy to implement this function. Right? So these are the two steps that are needed. Right? So this is going to be my f of h that I want to implement, because already from this observation you know that this f of h is interesting because it can prepare a quantum state that is close to the ground state, right? So I'm going to implement this using LCU. How do I do that? Well, you can there indeed exists an LCU decomposition of this function, and this you can think of the way we derive it is not important. What is important is indeed there exists an LCU decomposition of this function, and the unitaries here are time of evolution operator, right? And the lambda term, which is the sum of these weights, is a constant. You can prove that. And the maximum time evolution of the Hamiltonian is kind of proportional to square root of t, right? So if t that you need is kind of 1 over delta square, you would only need to evolve the Hamiltonian for 1 over delta time, right? This j times delta t at max could be m times delta t, which is kind of a log factor. So we can show that that the maximal time for which you need to evolve this Hamiltonian is something that is proportional to square root t, right? So indeed, for this LCU description of e to the minus h square is something that we are going to use, right? So what is the first thing to notice? Well, what are the UJs that we sample? Remember in our strategy? Well, these are now just time evolution operators, right? So we will assume access to these time evolution operators, right? So we'll just use our algorithm where the UJs are now just time evolution operators. So we'll just sample these unitaries according to the weight of their LCU coefficients, like I described, and the cost is going to be upper bounded by the maximal time evolution of h, right? Which we just estimated, right? You can also assume that you don't have access to the time evolution operator, but there's some quantum simulation algorithm that implements this quantity. And in that case, the cost will be upper bounded by the choice of the quantum simulation algorithm, right? So depends on what kind of quantum simulation algorithm you use. Okay, so our strategy is so let us first estimate what the circuit depth or the cost of each run of the algorithm is going to be. Well, as I said, the maximum time that you need to evolve this for is kind of square root of t. So it's kind of proportional to 1 over delta up to some log factor, right? So this is the cost of running the algorithm once, and the overall strategy is exactly the same as I had described, except that you are now the UJs that you are sampling are time evolution operators, right? Okay, so the strategy is again to run the algorithm twice. So first you obtain an accurate estimate of the norm, and then you obtain an accurate estimate mu of the expectation, and then you take its ratio and you are done, right? And the number of times that you have to repeat this algorithm is something like this. So it's norm of O square epsilon square. Forget this log factor. But the crucial thing is that it depends on 1 over eta to the power 4, where eta is this initial overlap factor. Okay? Now let us compare the performance of our algorithm with state-of-the-art techniques. All right. So on the left you have state-of-the-art techniques for ground state preparation, which can be leveraged to estimate expectation values. You can see that our circuit depths are lower. So we need circuit depths that are better by a factor of 1 over eta. We need far less ancilla qubits, but we do pay more in terms of classical repetitions, right? So, but this is fine because we are in the early fault-tolerant quantum era where our goal is to minimize circuit depths, have as low circuit depths as possible, even if it means paying for classical iterations, right? Okay, for quantum linear systems, I'll go briefly. What we do is we implement the expectation value with respect to the solution of quantum linear system, right? And let's say that we are given some Hamiltonian H, whose condition number, the ratio of the maximum and the minimum eigenvalues, are upper bounded by kappa, right? So suppose we are given some Hamiltonian and we know this value of kappa. All right. Then, our algorithm requires a circuit depth that is linear in kappa, right? And the number of iterations that we need scales as kappa to the 4. And so if you compare our method to existing techniques, our algorithm has an exponentially better circuit depth than the HHL algorithm. So if you look at the dependence on 1 over epsilon, it is exponentially better. It is also quadratically better in terms of kappa. All right. We also need 1 ancilla qubit, whereas the ancilla qubits needed in HHL algorithm is a lot because they perform phase estimation and so on. But of course, we pay again in terms of classical repetitions, which is fine. And there's also there's another algorithm by Childs, Kothari, and Soma from 2017, which uses linear combination of unitaries, but the standard procedure of linear combination of unitaries. And again, our circuit depths are better, quadratically better this time with respect to kappa, and requires far less ancilla qubits, does not involve sophisticated controlled operations, but and we pay more in terms of classical repetitions. All right. So to sum up, we can indeed use early fault-tolerant quantum computers to design useful quantum algorithms. I've given 2 applications here, but there are plenty, and one can in principle design quantum algorithms for using early fault-tolerant quantum computers now for a plethora of problems. Okay, so that here I come to the end of my talk. Thank you very much, and I'd be happy to take questions.
Thank you, Dr. Chakraborty, for this excellent talk. So we can open up for some questions.
I have a question.
Yeah.
In selecting V1, V2 from that D, the distribution. That's it. So are you selecting them randomly?
Yeah. So you are. Let me share the screen again. Okay. Can you see my screen?
No, it is shared.
Okay, it is shared. Okay, let me just go to the correct slide. So you are not doing it randomly, you are sampling it based on the weight of the LCO coefficients, right? So this is what you're doing. Where is this? Here it is. This is what you're doing, right? So you are sampling V1 and V2, right? Which are unitaries, right? So what are these unitaries? These are any UJ, right? So you are sampling any UJ proportional to this probability, right? So it's kind of CJ divided by lambda, right?
Okay.
Right, and this is why this is good, because the expected value of the sampling gives you the unitary that you sample from. Their expected value gives you the required LCU up to this 1 over lambda factor, right?
Okay. So it is more if you are using that unitary for more number of times, it's more probable. That's it. The CJ will be large.
No, but you are fine. No, the CJs are given to you, right? So the CJs are given. Lambda, yeah. So lambda is also known, right? Because the way you define the problem is like this. So you want to implement a function which is close to some linear combination of unitaries, right? So you have access to the UJs, right? You know what the CJs are, and as soon as you know what the CJs are, you know what lambda is, right? So you know both these quantities. So the CJs are fixed, lambda is fixed. Now you just sampled unitary according to this probability.
Okay, the probability CJ over lambda is the probability.
Yes, CJ over lambda is the probability. And any LCU description naturally gives you this kind of sampling ability.
Okay. So the standard at the last bottom slide somewhere, you are comparing this randomized sampling to standard LCU technique, and you are saying this is better. So how that is different from the way you are doing different from comparison?
So are you
the next one?
So is it this slide is good? The next one? This one?
Yeah.
Next
Here
one?
also the same
This
LCU
one?
algorithm. Right?
No, but we
63rd
require
slide.
only one ancilla qubit. 63rd slide, yeah. So we implement the same LCU algorithm, yes, but our circuit depths, right? The circuit depths are shorter by a factor of say kappa, right? Quadratically smaller. The ancilla required is less, right? We need only one, while there you need multiple. You don't need sophisticated controlled operations, right? So in the standard LCU procedure, if you remember, you need to implement controlled unitaries which are controlled on all the ancilla qubits. Here, because you have only one ancilla qubit, your operations are controlled only over one ancilla.
Okay.
So you have an advantage in terms of circuit. You have an advantage in terms of the ancilla. These are two restrictions that you have for early fault-tolerant quantum computers, right? So classical repetitions is not a problem because you can repeat this. You can run this short depth quantum circuit many times, but what you are limited by is the depth and the ancilla space.
Okay, thank you.
Thank you.
Any other questions? If not, I just wanted to ask one thing. I mean, this classical repetition values that you have, does this also take into account the variance due to sampling?
Yes. So every so what I mean by classical repetitions is that you're measuring, right? You're measuring and then you're getting some outcome, right? So you look at the variance of the outcome and then you use some sort of a bound like Houghton inequality to kind of estimate the number of classical repetitions you need so that the sample mean of your measurements converge to the actual mean.
Any more questions? Not, let us thank Dr. Chakraborty once more for this nice talk. And then this session comes to an end here. Break for lunch, I guess. Thank you, everyone.